All right, so here we go. We're doing number 3 here. So we've got this pulley. It's got a radius of r. It's 10 centimeters, 0.1 meters. And then we've got these 4 blocks that are hanging from it. Each block has a mass of 0.4 kilograms. All right, and question A is a little bit silly. It just says determine the tension in the cord. But notice the pulley's not doing anything right now. It's just hanging there, right? There's not going to be any motion because we've got equal mass on both sides. And so that just means that if you look at, one of these little systems here, let's swap colors out. What's going on, bud?
I brought all my music back.
Oh, good. From T-Bone's house?
Yes.
Excellent.
Now I can practice my guitar.
Right on. You know what we got to do, bud, is we got to plug this back into the PlayStation and play, what's it called, Rocksmith or whatever it is?
Right.
Like,
Yeah, but that's not going to help me with the songs I'm actually practicing.
no, but it'll help you practice your fingering, which is good.
Levi's taught me some things to help me do that.
Okay. Hey, will you do me a favor when you go upstairs? Levi offered to either come over or Skype in some lessons with you this week. Will you go ask Mommy if she wants me to set that up with him?
Whoops.
Sorry, guys.
Ow.
I'm not starting this over. You're just going to have to deal with this. Welcome to the apocalypse. All right. So, will you ask Mommy
Yeah.
if she wants either... Which one of those is she most comfortable with? Okay?
What does Skype mean?
Skype, it's like a video conference. So it would be he sitting at home,
So what was
showing
the
you,
other one?
or him coming here.
Okay.
But I don't know if we're supposed to have people over, what with the zombie apocalypse and all. Cool?
Yeah.
All right.
Mommy?
Okay, sorry. Unfortunately, I don't have editing software. I suppose I could start over. Should I start over? No, we're going to just do it. Okay. Okay. So, this thing isn't moving, right? So, within that little red blob there, we've got a mass of 0.8 kilograms. Gravity is going to pull it down with a force of 7.84 newtons. And since nothing's moving, that means our tension force has got to be 7.84 newtons. So that's all you had to do for part A. Okay? Sorry, again, looking to see how bad the glare is. All right, now part B, it says one block is now removed from the right and hung on the left. Okay?
She doesn't care.
She doesn't care? Okay, cool. I will sort it out. So we're going to take one off of the right and hang it from the left. So that means that when we're done, we're going to have 1, 2, 3 masses on this side and only 1 mass on this side, right? Okay. So let's just do this. I'm partly to save room. Here's what we're going to end up with. We're going to have 1.2 kilograms on this side and just 0.4 kilograms on this side. What are the odds you can read that? I guess it's not terrible. I'm sorry I keep sticking my ugly face into the camera, but I'm just trying to make sure you guys can read all this. All right. So that happens. Let's see. So we move them over, and then it says when the system is released, the 3 blocks on the left accelerate down with an acceleration of 2.45 meters per second squared. And then you got to find the tension in the 2 strings and the rotational inertia of the pulley. All right. So here's the deal. This time our pulley actually has mass. It's got rotational inertia. Okay. So let's do this. So I feel like I want to use some colors here. So our acceleration is going to be 2.45 meters per second squared. All right, and so what we need to find is the tension in the ropes and the rotational inertia of the pulley. All right, so basically what this boils down to is, as I've said, anytime you have a problem like this with moving and rotating parts, you want to write a net force equals net force equation for the parts that are moving linearly, and then a net torque equals net torque equation for the ones that are rotating, right? So I'm going to write a net force equals net force equation for the guy on the left, all right? So left. So let's make our free body diagram. So the force of gravity of that guy on the left ends up being 11.76 meters per second squared. And then we've got this tension. And I know that my acceleration is down, it's 2.45 meters per second squared. So I'm going to choose the direction of acceleration to be positive. So this is going to be positive, which means my tension on this particular drawing is going to be negative, okay? So now I'm just going to go, all right, well, net force equals net force. So The mass of the block on the left is 1.2 kilograms. Acceleration is 2.45 meters per second squared. That's got to equal my, oops, sorry, I put meters per second squared. This is supposed to be newtons. Minus our tension, right? Or plus our tension, and then you'll get a negative, however you want to think of that. Okay? So, algebraify this, and the force of tension, let's call this FTL, as in force of tension on the left. So that gives you 8.82. Oh, they called that T3, didn't they? Sorry about that. So that gives you 8.82 newtons. All right, so let's make a note of that. We know that our tension over here, tension 3, and they call this tension 1. So tension 3 over here is 8.82 newtons. Cool? All right, so that's the tension for the cable on the left, tension number 3. Let's make a little note that we figured that out. Tension 3 was 8.82 newtons. Okay, now for the one on the right, I'm going to kind of do the same thing. My force of gravity is 0.4 times 9.8, so 3.92 newtons. This time my acceleration is up. And so, because my gravity is working against that, I need to make that negative, all right? Again, I try as much as I can to choose whatever direction the system is accelerating in. I try to keep that positive. All right, and then we're going to find the force of tension for a cable on the right. The worksheet calls that T1. And so now again, we're just going to do net force equals net force. So net force equals net force. So 0.4 times 2.45 equals tension 1 minus 3.92. And solve for tension 1. And if you solve that, you get 4.9 newtons. Okay, so there's tension number 1, 4.9 newtons. All right? Again, just net force equals net force. All right, so then the last part of the question asks us about the rotational inertia of the pulley. All right, well, that rotational inertia is going to depend on the torque, right? Well, so how fast it moves is related to the torque and the rotational inertia, right? I guess what I'm trying to get at here is because the pulley's rotating, we want to consider torque instead of force, okay? So let's make a new free body diagram for the pulley. So here's the pulley. And there are actually 3 forces on the pulley, right? There's tension 3 pulling it down, 8.82 newtons. We got tension 1 pulling it over here, 4.9 newtons. Our acceleration is going to be this way. Now, where's the third force? Well, technically there's a support force at the axle, right, which is enough to support the weight of the pulley plus these 2 tension forces, all right? But I'm going to not worry about it because that support force, let's just call it Fs, is not going to produce any torque about our pivot point, right? Okay? And we'd have to know what the mass of the pulley was to find that, okay? So here we go. Net torque equals net torque. So let's see, we're trying to find I times alpha equals the torque from tension 3 plus the torque from tension 1. So I is what we're looking for. Let's leave alpha alone. Well, we can do alpha, right? The idea is the string is not slipping on the pulley. We know our linear acceleration of the string, so that means that A is alpha r, so that means alpha is A over r, right? For a point on the outside edge of the pulley. So that's going to be 2.45 is A over our radius, which is 0.1. Okay? Yeah, the r's are not going to cancel in this problem, are they? Yeah, because we don't know the mass of the pulley. Okay, so that's that. A over alpha equals the torque from pulley 3 is 8.82 times 0.1 plus the torque from pulley 1, or from tension 1, sorry, I said pulley. Torque from tension 3 and torque from tension 1. All right. Now, remember, right now I've got these both as being positive, as though they were working, with one another. But they're not. So one of them has to be negative. Well, the idea is, remember I talked about signs here, right? So I've decided to make this way positive. And it looks like this guy is going to contribute to positive torque, which means I got to make this one negative. Okay? Oh, sorry, sound effects, gross. All right, and so at this point, it's just algebra, right? So let's see. So if you simplify this, oh, I just wrote the answer down on my paper. Okay. So anyway, yeah. So I mean, you got. I don't know why I'm doing this. All right. So simplify this side, simplify, and then divide, and your rotational inertia turns out to be 0.016 kilogram meters squared. Okay. Net torque equals net torque. Net force equals net force. Boom.